Hi, welcome to this video. My name is Christoph Völker and I'm a researcher in a junior research group at BAM called Materials Characterization and Informatics for Sustainable Building Materials. And today we're going to talk about the exciting world of AI-driven materials design. In the first part, I want to give you some background and some motivation for you to find out who this could be for. In the second part, I will introduce our software tool SLAMD. In this hands-on session, you will understand how to use AI-driven materials design in the lab to design more sustainable and environmental-friendly materials. Let's get going. Okay, so let's get started with data-driven materials design for cementitious materials. And you might be wondering, why do we need a new design approach? Let's have a look. The truth is, construction materials are in a major sustainability crisis. The production of cement alone amounts for 8% of man-made CO2 emissions. And the ecological question is thus far unresolved. You might think, why don't we just build everything made from wood? The problem is, we need to find a solution that works at scale. If we want to replace 20% of cementitious materials with wood, we would need to plant a forest 1.5 times the size of India. And we are already using more wood than we produce. Furthermore, 60% of all wastes come from the construction industry. This is a big number, but when you think about 50% of everything mankind produces is concrete, this number starts to make a lot of sense. The problem is that these materials are mostly sourced from primary resources, which are used in the construction process, and at the end of the lifetime, buildings are just being demolished and the waste ends up in landfills. So there's a huge circularity gap that requires closing. The thing is, waste is a material with unknown properties. And if we could enrich waste with information, we can transform waste into viable resources. So here's an undeniable truth. That is true for concrete, but also for many other materials. If we want to increase the performance in terms of circularity, CO2 efficiency, and cost efficiency, this comes at the price of complexity, which means resources are less and less pure, the material composition is getting more complex, and local supply chains make planning much harder. So this is how this complexity trade-off looks for concrete. If we want to reduce the ecological impact, the complexity of the formulation of the material increases. From initial optimizations with higher packing density of the aggregates, we are now moving to a world in which we replace the cementitious materials with supplements and also try to use secondary resources as aggregates. So this is the formulation complexity, but there is a second complexity that comes from the precursors themselves. If you look at this oxide diagram, you will notice that Portland cement has a very defined composition, whereas alternative materials such as waste slags, fly ashes, or natural puzzolans are much more scattered in their composition. This means that one day your waste slag could have a composition in this corner, and on the next day it could be here. But we can act on this complexity by combining various precursors with each other, and then find materials in this combined design space which fulfill the requirements we have. And this is where the AI approach comes in. The AI's purpose is to navigate towards these materials as quickly as possible and as effective as possible. But how does it work? The challenge lies in navigating these complexities. Previously, our approach has been to sample a representative set of formulations. Basically, take one formulation from each corner of the design space. The problem is that the whole concept of representative data does not exist for complex problems. This has to do with the weird geometry of high-dimensional spaces. So It is not a problem of our ignorance or a problem that we could solve with collecting more data. It is a fundamental problem of complex systems, such as sustainable materials. The AI approach, on the other hand, works differently. Here, we try to navigate the complexity, which means we start out at a given point and then systematically work ourselves towards formulations that work and meet our requirements. This way, we can ignore a huge part of the design space and only focus on the materials that are viable for our purposes. So AI-driven materials design navigates towards the target in short feedback cycles. You collect data, you train a model, which shows you the next data point to collect. And this updated cycle helps you to navigate quickly towards your target. Whereas in screening, you collect your representative data sample, and if you're not able to find a good material, what are you going to do in the next round? You could try to enhance the data set, but there's no targeted way to reach your specification. How do we know that it works? Well, we measured it. In a large-scale case study, we conducted more than 10,000 simulated design runs in order to measure the time an AI-driven approach requires to find predefined materials. Here's how it works. Basically, you collect data from the literature, so this is real lab data that scientists have reported. And then within this data set, specify a material of interest, for instance, a high-performance material. We then initialize the AI with a randomly selected training data set and count how many updates the AI requires in order to find the specified materials. And we don't just do this once, we do this over multiple runs with randomized initial conditions. And this gives us a distribution of the development time required of the AI approach to find these specified materials. And here you could analyze, for instance, the mean time, or you could even analyze the 90% success probability, which means that in 90% of the cases, the material was even faster discovered. And this measure is very robust. It's a lower bound measure of the performance. And we did this over 9 large data sets in more than 10,000 experiments. And we measured an acceleration of up to 40 times compared to screening the whole data. So 40 times, this is a really big number. You can think of it as being 40 times more efficient than not using AI. Another benchmark that we looked at is random sampling, so basically relying on luck. This is a common benchmark, and even compared to this benchmark, which is more efficient than, of course, screening the full multitude of formulations, even here we have an acceleration of 10 times. So AI is 10 times more efficient than luck. But what do these numbers mean? 10 times, 40 times, these are big numbers. Does it mean that we're just ready in the lab 10 times faster? Well, actually, we aim to use this higher efficiency to increase the performance. In other words, we can now investigate materials that are 10 times more complex than previously. And to do this, we developed a design software. The design software is called SLAMD. It's an open source software. It's platform independent. You can access it worldwide on any device. The access is free, and you just have to follow this link. And this software combines a digital lab twin. Think of it as a tool to create these caves full of formulations, and an AI optimization tool. So basically a tool that helps you navigate this cave. So in the next section, let's have a look at a hands-on example on how to design sustainable materials with our software tool.